Hello and welcome to the University of Southampton School of Mathematics Virtual Open Day. I'm Nick Wright, my area is pure mathematics. I'm also the admissions tutor for mathematics, so if you apply for a place here and then things get a bit more back to normal and you're actually able to come and physically visit, I'm one of the people who you're very likely to see. So the idea of this lecture here, it's a taste of some of the mathematics that you'll learn here at Southampton. Hopefully it'll be kind of fun and interesting. I'm going to talk about the mathematics of vectors and how this applies to the theory of sound. Now this connects with all sorts of areas of mathematics. So if we're trying to understand sound, this relates to calculus, it relates to differential equations. But it also relates to linear algebra, meaning vectors and matrices and things like that. And that's the area that's going to be my focus today.
Let's start with sound waves. We've all seen a picture of a sound wave. We know roughly what it looks like. So the horizontal axis is time. This is a recording actually of someone playing the violin. We're going to measure time in milliseconds. So here we've actually got 5 seconds, 5,000 milliseconds. But to see the shape of the wave, we have to zoom in. We have to take a very small part of this picture and expand it out. So now we're looking at merely 2 or 3 milliseconds of sound, and you can see the detail of the wave at this point. Mathematically, the simplest example of a sound is a sine wave. So this is just a sine function. So we've got here y equals a sine 2 pi ft, t is time, f is the frequency, so that's the pitch or note of your sound, and a is the amplitude, so sort of how tall the wave is. So now let's look at some sine waves of varying frequencies. So we're going to start with this one. That's a middle C, and that's a frequency of 261.6256. The digits go on forever, in fact. This next one, that's the A above middle C, that's 440 hertz. Now what we've done here is we've kind of squashed the wave together, we've increased the frequency so it's oscillating more rapidly. And then the third one here, the A below middle C, that's 220 hertz. Now notice that the A's are nice round numbers, that's because the frequencies of notes are really defined relative to A. The A above middle C is defined to be 440 hertz and everything else is done relative to that. The two A's differ by a factor of 2, and that's because an octave in music is a factor of 2. And so when you double the frequency, you're going up by an octave. When you halve the frequency, you're going down by an octave. It's worth thinking about what would it mean to go half up or down half an octave. Because the change is multiplicative, the number or frequency halfway between 220 and 440, that's not going to be 330 hertz, because if I'm going up by a factor of 1.5, if I do that twice, I'll have overshot. I'll have gone up by a factor of 2.25. So actually, the factor which will be half an octave is actually a square root of 2. 2 of those multiplied together, giving you a whole octave. C is actually a quarter of an octave up from an A, and so that's actually a fourth root of 2. And if you get your calculator out and try this, 220 hertz, multiply that by a fourth root of 2, you will get this funny 261.6256 figure. Now the sine waves themselves, they don't really sound very good. They're not particularly pleasant to listen to. So to make it a bit more interesting, here's one which combines 2 sine waves. I personally think this one looks or sounds a little bit like an old 80s electric organ. Maybe that the 80s electric organ worked precisely by combining 2 sine waves together. So when I do this combination, what am I really doing? I've got one sine wave, so that's the blue one in the diagram, and then I'm adding a sine wave which has got 2 times the frequency of the original one. It's going up and down twice as fast, but only half the amplitude. And so at the beginning, where they're both positive, these things reinforce, and then you start to get cancellation, and then when they're both negative, they both again reinforce again. If we want to make sort of slightly more interesting sounds, we can add several sine waves together. So this next one here, this is basically following the pattern. I start with one frequency and then I add twice the frequency, and then I'm doing 3 times and 4 times and 5 times the frequency, but at each stage halving the amplitude. Of course, time is a continuous variable, but when we plot a sound wave, or when we store it on the computer or on your phone, or indeed when being a bit old-fashioned, we read it off a CD, then we can only look at a discrete finite set of values. This is called sampling. We sample the sound wave at some very, very large number of times per second. And for a CD, for example, it's 44,100 times per second. We just look at the values at those finite set of times, and we don't worry about the values in between. This process of discrete sampling is where the term sample comes from in music, meaning sort of a recording of someone's song or what have you. Now, the human ear can hear ranges of sounds from about 20 hertz up to 22,000 hertz. And that's where this 44,100 comes from. You need a number that's just a little bit bigger than twice the maximal frequency that you're trying to record.
So what has all this got to do with vectors? Well, let's start off by asking ourselves, what is a vector? What do I mean by vector? If I had to describe a vector to someone who'd never come across the concept before, what would I say? Well, I might start by drawing a picture and basically say, well, a vector is some sort of arrow. It points in some direction here. If I want to be a bit more mathematical, I might give a list of coordinates. So, 0, 1, for instance, meaning I have 0 component horizontally and a vertical component of 1. If I want to be a little bit more conceptual, I could talk about a vector as being a quantity that has magnitude and direction. Now, there isn't a single right answer here. They're all really different aspects of this same idea. Now, when I describe the magnitude, that's easy, it's just 1. And for direction, I need to say relative to something else. So, for instance, it's 1 in the direction of the y-axis. And actually, the coordinates, as we saw, were also relative. That's in terms of the axes. And I might also want to think about measuring the vector relative to some different set of axes. So, suppose I want to resolve the vector into components not horizontally and vertically, but in some other direction. Say I take an angle π/4 to the axes. So I have 2 vectors here. I've got the vector u, which goes in that direction, and the vector v, which goes in this direction. They're both π/4 from the axes, so their coordinates are given by cosine π/4 and sine π/4, and then for v, it's minus sine π/4 and cosine π/4. You might remember that cosine and sine of π/4 are actually equal. Both of them are just 1 over the square root of 2, or maybe you've seen the square root of 2 over 2. That's the same thing. Now, if I want to resolve the vector into its components, then there's a useful tool I can use, which is something called the dot product. You might see this in your A-levels. If you haven't seen it, don't worry. It's actually really quite simple to explain how you do the dot product, but also very useful. So if I have 2 vectors, here I'm just taking 2-dimensional vectors. So one of them's PQ, the other one's XY. I just multiply the first component together, so I have P times X, and the same thing with the second component, Q times Y, and I add them up. It's a very simple rule. But it's very useful because it's got this interesting geometrical interpretation. If I take the dot product of 2 vectors A and B, what I get is the length of A times the length of B times the cosine of the angle between the 2 of them. Now, in particular, suppose one of those vectors is a unit vector, a vector with length 1. Then, well, when I do the dot product, I just get the length of the other vector times cosine of the angle. But now, if I think about the right triangle that I've drawn here, so I've got the u direction, and then I've got the a vector, and then I drop a perpendicular from the a vector onto the u direction. Well, the component of a in the direction of u is exactly a cosine theta, the length of a cosine theta. So the dot product computes the components for us. And that means I can write my original vector, the vertical one, as some number of u's times some number of v's. And the number of u's and the number of v's that I need is simply given by the dot products. I take the dot product of u with my 0, 1 vector, and that means I take 0 times 1 over root 2, well that's 0, and then I take 1 times 1 over root 2, that's 1 over root 2. So that's one dot product. The other dot product actually turns out to be the same thing, because it's only depending on the second component of the u's and v's, and those are both 1 over root 2. And so this means I can build my 0, 1 vector as 1 over root 2 times u plus 1 over root 2 times v.
So now let's get back to sound waves and sampling. When I sample a sound wave, what I get as my data is just some list of numbers. Those are supposed to be the amplitudes at various different sort of small time intervals. But if I have a list of numbers, I can think of it as being a vector. Now, normally you're used to thinking of vectors with 2 or 3 coordinates, and now we're going to have probably thousands of them. But at the end of the day, the algebra behind it is kind of similar. Maybe we want a computer to actually do the calculations for us because it's going to be quite long-winded, but the ideas are kind of the same. And remember, when we talked about vectors, we said that there are different coordinate systems, and the same thing is true here with these samples. So when the sample comes to us, it comes in one coordinate system. So the first coordinate is the first sample, the second coordinate is the second sample, and basically each coordinate corresponds to the amplitude at a different time. But here's another coordinate system we might use. We might try to use some sort of coordinate system based on frequency so that we can split the waves out into their separate frequencies. Now, our motto from thinking about the vectors is that dot products compute components for us. And the same thing is going to be true here. We're going to use dot products to compute frequency components of a sound. So, to be specific, let's look at the sine wave again. So we've got sine of 2 pi ft. Remember, f here is the frequency. Now, normally frequency is measured in hertz. That means the total number of cycles, the total number of oscillations that we have per second. And t there is then measured in seconds. So now t is going to, if I have n samples taken over 1 second, then t is going to be 1 over n, 2 over n, 3 over n, and so forth. So I'm evaluating sine of 2 pi ft at t is 1 over n, 2 over n, and so forth. So I get this long vector with n entries in it. Now, to make this a little bit simpler, I'm going to define a new frequency, capital F, which is little f divided by n. And now I'm just changing the units. Instead of asking about the number of cycles per second, I'm asking about the number of cycles per sample. Now, actually, if I've got, 3 cycles per sample, this is going to be no use whatsoever because sampling is going to miss, 2 out of 3 cycles. So the number of cycles per sample is going to be something, or needs to be something, that's less than 1. Really, we want several samples per cycle rather than several cycles per sample. So this f is going to be some fraction that's less than 1, the capital F. Little f should be an integer. That's because we want things to sort of match up. If I get to the end of my 1 second clip, I want to have completed a full number of these sine waves. So little f needs to be an integer, and that means that capital F can be 0, 1 over n, 2 over n, and so forth. And it can go up to a half. The reason we can't go beyond a half is that if I swap capital F between, so say I have a number bigger than a half, like 0.7 in this example, if I look at the frequency of 0.7 and the frequency of 1 minus that, so 0.3, when I take those samples, I will get exactly the same value. Well, actually, I get it with a change of sign. This is because sine of 2 pi n times 1 minus f, well, sine of 2 pi n actually is just 0. made 2 pi n, we've made n full cycles. So I'm just left with sine of 2 pi n times minus f. And this picture illustrates the problem. If I look at the sine with frequency 0.7, that's the green one, the faster one, and I compare it with the sine with frequency 0.3, but negated, it's turned upside down, so it starts off by going down and then up and so on. When I evaluate at those discrete points, that's what the red lines are indicating there, the individual samples. I will get exactly the same thing from the blue and from the green. So if I have this higher frequency green wave and I just look at those discrete points, it looks like I've just got this lower frequency blue wave. And so that's why our capital F had better not be any more than a half. And actually, going back to what we were saying earlier, the human ear can hear up to 22,000 hertz, and so our sampling rate needs to be double that, because if I'm sampling 22,000 hertz, but I'm sampling 44,000 times per second, then that gives me a value of capital F equals a half, which is the biggest we're allowing it to be. So as a variant on this, we might replace the sine function with the cosine function. But actually this gives us a sound that really kind of sounds the same to us, because what we're doing here is, the cosine function and the sine function you just get from one to the other by shifting them a little bit. All I'm doing is I'm shifting the start time by 1/4 of the period, so 1/4f here. Of course, I could shift by any number from 1 up to capital N here, and so at first sight it looks like I've got n different vectors, all with the same frequency. But actually I only need to think about the sine vector and the cosine vector, and I can build all the other ones from that. So that uses one of these trig identities that you probably don't really remember, but trust me, this is the formula. Sine of a plus b is sine a cos b plus cos a sine b. I've written it as cos b sine a instead of the other way around, just because of how I'm going to use it. So looking at my vector here, I've got, say, sine of, let's take the third coordinate here. I've got sine of 2 pi times 3f plus 2 pi times f. And then the formula says I can write that as cosine of 2 pi f times sine of 2 pi times 3f, and then plus the same thing but with the a's and b's switched around. And notice that all the way through this I'm going to get a cosine 2 pi f term plus a sine 2 pi f term, and then I'm going to get varying terms of sine 2 pi 3f and cosine 2 pi 3f and so forth. So putting this all together, this one vector, which is, I shifted my start time by 1, I can write that as the sine vector that I had times some scalar, which is given by this cosine, plus the cosine vector times some scalar, which is the sine. So again, this is a case of taking vectors and resolving them into components. We have this vector, which was I took the sine wave and I shifted it by 1. Now what I see is I can resolve it into two components, a sine component and a cosine component. Of course I could shift by 2 or 3 or 4 and so on, and all that's going to do is change those coefficients that I put at the front of these two vectors. Fourier theory is the idea that any time you have something that's periodic, that repeats, it can be built out of sines and cosines. Now, the fact that you can do this for absolutely anything that repeats is really a remarkable fact. So, in terms of vectors, what we're saying is that absolutely any vector that you can write down can be built out of sines and cosines of various frequencies. So, to do this, we're going to use the dot product. For that, remember, we wanted to have unit length vectors, so what we're going to do is we're going to take the sines and cosines and rescale them to make them unit length. Turns out the factor we need is the square root of 2 over n. That's another of these trig identities. I'll call it an exercise and leave you to work that out yourself if you're really keen. The hint is you use the double angle formula. So to summarise, how many vectors have we got? We said that there are actually n over 2 plus 1 possible frequencies, ranging from 0 up to a half. So n over 2 would range, say, from 1 over n up to a half, but we've got 0 thrown in there as well. So that's like an extra one. And for each of those frequencies, I've got 2 vectors, the cosine one and the sine one. So in total, that's n plus 2 vectors. That's actually more than we need because we've only got sort of n coordinates. But actually, it turns out exactly 2 of those vectors we've written down as 0. If I take the frequency f to be 0, and I put that into the sine, I'm just evaluating sine of 0 repeatedly. That's 0. On the other hand, if I take the frequency f to be a half, it's fine in the cosine one, but in the sine one, again, I'm going to get 0. I have sine of 2 pi n times a half. That just means I'm evaluating sine of pi times n. And of course, again, those are all the 0 points of the sine function. So that gives me exactly n vectors now, once I throw those 2 away. And that's exactly the number of vectors I need to build any other vector. Now that we've learned how it is that we can decompose one of these sound waves into its component frequencies in terms of sines and cosines, let's look at an example. The first example we're going to look at is the square wave. Now, a square wave is a very simple wave. It just alternates between some positive value and the same thing but negated in this sort of kind of square shape. What we have here is a square wave with frequency 440 Hz. Remember, that's the A above middle C. And to decompose it into the component sines and cosines, what we need to do is to compute a bunch of dot products. The dot products of each of these sines and each of these cosines. So for the cosines, we can work out what that is fairly easily. What we see is that, remember the rule for the dot product, each term, each sample in our square wave vector is multiplied against the corresponding sample in the cosine vector, and then we add all of those up. But in the square wave, the terms we're multiplying by are basically either plus 1 or minus 1, up to some rescaling. And so what I've done here is I've drawn the cosine that we're trying to take the product with, but I've drawn it alternately in red and blue. So blue indicates where the cosine is multiplied by a plus 1, and red where it's multiplied by a minus 1. And you see the blue section at the beginning and the red section at the end basically look the same, apart from their colour. Right, of course, one is reversed from the other one. But when we add these terms together, when we add the red term and the blue term, we're going to get 0 because the red term is multiplied by minus 1 and the blue term is multiplied by plus 1. So the dot product is 0. It's going to total 0. And if I have a cosine with higher frequency, so here it's oscillating twice as fast, we're going to get the same answer. We're going to get 0 again. Now, for the sines, it's a little bit more complicated, and remember, actually, we've got to look at 22,000 different frequencies if we're sampling at 44,000 Hz. So, in principle, we've got 22,000 terms to compute. Of course, we can reduce it down, we can simplify this, but just to save time, we're going to put it into the computer, and the computer will tell us the answer. And here it is. Again, for most of the sine terms, the dot product is again going to be 0. But we just see spikes at a certain discrete set of frequencies. Now, what are those frequencies? Well, the first of those frequencies is 440 Hz. That was the frequency of our square wave. And then the next one is not 2, but 3 times that. Okay, so we have here 3 times 440 Hz. And then the next one is not 4, but 5 times that 440 Hz frequency. So we get basically that original base frequency, but then multiplied by 1, 3, 5, 7, all the odd multiples. And those are where we get the spikes.
Our next examples are musical instruments. For each one, I've sampled a single note and then looped it to give us something that we can Fourier transform. We have a violin, a cello, and a French horn.
Here are pictures of the sound waves. In no particular order, we've got a French horn, we've got a cello, we've got a violin. Your challenge is to try and work out which is which. Now, it's not so obvious just looking at the sound waves. If I move to the frequency analysis, on the other hand, now the differences become rather more striking. So, what I've done here, I've not separated out the sines and cosines, I've just shown the total amplitude for each given frequency, sort of combining the sine and cosine terms together here. The first thing we notice is that, much like we have with the square wave, there's kind of a first frequency that we see, and then we get various multiples of that frequency. That's really the characteristic of sort of something like a musical instrument. That is the frequency that you hear of that instrument, you know, whether it's an A or a C or what have you. Now, the other thing that we notice is that the middle instrument, the second one there, is definitely kind of an odd one out. It's rather different to the other two. By the time I've got the first two frequencies of this, so the first frequency has this amplitude and then the second frequency has that amplitude, but once I've got those two, that's actually more or less the whole wave. All the other frequencies have very low amplitude. So that definitely looks like the odd one out, and sure enough, yes, that one really is the French horn. Now, what about the first and the third? That's the cello and the violin. Which one is which? Well, again, there are sort of similarities and there are differences. If I look at that first one, you know, there's kind of the frequencies jump up and down a little bit. There's no particular spike there, whereas in the last one, a bit like the French horn, there is this big spike on that second frequency. So that's sort of perhaps a key difference between these two instruments in terms of their sound. The other thing that you probably notice is that when I compare the one at the top with the one at the bottom, actually the spikes are much closer together at the one at the bottom. In fact, we're getting essentially twice as many spikes. And that means that our sort of lowest frequency that we have here is definitely a little bit lower. So we have violin, we have French horn, and we have cello.
Here's another application of Fourier theory. The clip you just heard is a recording of Lewis Hamilton's engine from the Brazilian Grand Prix last year. At the time Lewis is running in third place, he's chasing down Pierre Gasly, who's currently in second in the Toro Rosso. Now, we hear that Lewis is accelerating, but what else can we tell from analysing the sound here? Well, I'm not going to take the whole sound, I'm just going to take the end of it when the revs are at their highest, and I'm going to loop that to give us something that we can Fourier transform. So here's the sound that we're actually going to transform. And what we're going to do is work out its decomposition in terms of sines and cosines, or more precisely, the computer's going to work that out for us. So here are the graphs. The first one, the blue graph, that's basically telling you the amplitude for each of the cosines. So the cosines are multiplied by those numbers indicated on the blue graph, which of course they may be positive or negative because we can of course negate the cosine. Similarly, the sines are multiplied by the frequencies that we see in red there. Now, what's noticeable is that both the sines and the cosines have a big spike there at 660 Hertz. So what does that tell us? Well, the engine, obviously, a large part of the noise from the engine is the firing of the cylinders. So this big spike at 660 Hertz, that's telling us how regularly, how frequently the cylinders are firing. Now, Formula 1 engines are V6s, that means
the engine has 6 cylinders. So if the cylinders are firing 660 times per second, that means each individual cylinder is firing 110 times a second, giving us 660 as the total. Now, a very, very small amount of information about how engines work here. These engines are what are called 4-stroke. That means that it takes 4 movements of the piston, that's in and out again, for each firing of the cylinder. The first movement is where the fuel is drawn into the cylinder and compressed, and then the second movement is actually the ignition, followed by the exhaust gases. So, all in all, what that tells you is that if each cylinder is firing 110 times per second, the engine has a full revolution 220 times per second. Well, RPM means revs per minute, so we just have to multiply that by a factor of 60 to find out what the RPM is for the engine. So that tells us that actually Lewis Hamilton's engine at the top end of the revs is currently running at 13,200 revolutions per minute. Now, that's kind of interesting. In particular, it will be interesting to Pierre Gasly to know this, because that probably means Lewis has turned the engine up a little bit. Formula One engines, they don't usually run at their maximum revs because they need to save the engines for future races. The engines have to last a certain period of time. And so a typical race RPM might be, say, 12,000. The fact that Lewis has turned it up to 13,000 plus it indicates that they are actually really pushing hard to try and catch Gasly. Now, of course, the fact that I can do this means that Formula One teams can do this as well, and indeed sound analysis of, this is a very basic example. They, of course, use much more advanced techniques looking at many of the frequencies, not just this one big spike. But these ideas of sound analysis are used in Formula One to monitor what your opposing teams are doing.
Thank you for listening. I hope it's been interesting and inspiring. If you do have any questions about our programs or you want to know more, please do get in touch.